Welcome to linear systems of differential equations. So definition, system, we're going to stick with linear first order systems. So first order system of differential equations is said to be linear if it can be written in the form y1 prime is equal to a11 of t times y1 plus all the way up through a1n of t times yn plus f1 of t all the way through yn prime is equal to an1 of t y1 plus up through ann of t yn plus fn of t. Note, this is written in a format that lends itself perfectly to matrices. So note, a linear system, a linear first order system can be rewritten with matrices. So we would have essentially y1 through yn vector, and then take the derivative of that whole vector, so derivative of every row, is equal to, we take the matrix a11 of t through a1n of t for our first row, all the way down through an1 of t through ann of t for our last row. That matrix is being then multiplying the vector y1 through yn. And then we add on the vector f1 of t down through fn of t. So in other words, we often write this as the vector y prime is equal to the matrix A of t times the vector y plus the vector f of t. We call A of t the coefficient matrix. And we call f of t the forcing vector, forcing functions. We get essentially the same existence and uniqueness theorem we have seen before. So a first order linear let's do an IVP with first order linear system. So an IVP with first order linear system, y prime is equal to a of t y plus f of t, where y and f are both vectors and a is matrix, with vector y of t naught is equal to vector k, let's call that vector k naught. This system has a unique solution on the open interval AB containing K naught, containing T naught. If each of the subfunctions of AT is continuous on AB. So if A of T are a matrix, or in other words, each A sub ij of T is continuous on AB. So this is essentially, and our vector f of T is also continuous on AB. So this is, as I said, essentially the same conditions we've had for all of our existence and uniqueness theorems for linear differential equations. So for our first order linear system, we just need all of those coefficient functions to be continuous, as well as our forcing functions. So let's go ahead and consider the IVP. Y1 prime is equal to 1 over t plus 3 times y1 minus 2y2 plus 3t. And y2 prime is equal to 2t times y1 plus 4 over t minus 2 times y2 minus t squared, with initial conditions y1 of 0 equals 2 and y2 of 0 is negative 1. So the first thing we're to do is to rewrite this IVP in matrix form and then determine the interval over which a unique solution is guaranteed. So in matrix form, we will have y1, y2, that whole vector prime is equal to our coefficient matrix. We should have 1 over t plus 3, and then a negative 2, and then 2t. So 1 over t plus 3 and negative 2 forms our first row, and then 2t and 4 over t minus 2 forms our second row. That's multiplying y1, y2, the vector. And then we will add on our forcing functions. So we have a 3t as our first row and negative t squared as our second row. Furthermore, our initial conditions can be written y1, y2 evaluated at 0 is equal to 2, negative 1. So this is rewriting our system of matrices. We just need to check that all the functions in our coefficient matrix are continuous and the functions in our forcing vector are continuous. So if we focus on our continuous matrix, so 1 over t plus 3 is discontinuous. at t equals -3. 4 over t minus 2 is discontinuous at t equals 2. And then all of our other functions, -2, 2t, 3t, and -t squared, are all continuous everywhere. Oops. Everywhere. So if we looked at a number line, our only problem points are at -3 and 2 are problem points. And then we're interested in 0 as our initial condition. So here's our T naught is between -3 and 2. And so this tells us then that we have a unique solution on the open interval from -3 to 2. So this is sort of the basics of linear first order systems.